Please take your seats. Take your seat. Before going on with the survey of the previous lecture, I would ask, since I think I'm one of the oldest, I have the right to speak now and thank for the organization of this wonderful school. Thank Itala, Walter, the people at Clay around Itala, around exactly as this funzionario this morning said with wonderful words in English. The same words I would say to Itala and all the people who work for this great undertaking, enterprise, which is unique because so many people covered by every expense for a long time from everywhere in the world is really unique. And I will not insist on what is for me personally, it's a wonderful experience. I think it's the 20th time I'm in Brazil. This is the time where I could teach, which is very important. So Itala and everybody who worked on this great event, many thanks. Okay. Molto obrigado. In the fourth lecture, we did something which is suitable to prepare the material that may be useful to Marcelo in his lecture after. Yes, yeah, and you're coming from Sao Paulo, I imagine, so driving hard along. Okay, thank you very much. We prepared the material. I had to rearrange the lecture, so if there are errors in precision, please stand up and say this is wrong, so that I can correct myself and the lecture and be more careful in revising the lectures. The first thing is this heavy, but not so much given the importance of the definition contained in these few lines. There is a small object, the truth values, full of structure, topological order, algebra. There is a large object built on by variables and connectives, by syntax, a syntax which is non-ambiguous so that you can write and express yourself to the computer. And this is the free algebra of formulas, which has the crucial freeness property that whatever map function you send from the variables to the truth values, it is uniquely extendable to a homomorphism. So a map that goes to paradise and becomes a homomorphism of the algebra of formulas into the super rich algebra, but small, of truth values. And then you define tautologies, equivalence classes of formulas, which are treated equally by each homomorphism. This is equivalence. Formulas, which are syntactic objects, modulo, divided by equivalence, are a very rich structure, algebraic, order theoretic, sometimes topological. Is the algebra of that logic. We are doing algebraizable logics, okay? Polish minimalist style. The minimality is here. And when you have tautologies, and when you have equivalence, you have the algebras, you can define consequence. This is a subtle point on which I will insist today about which quotients to take. And then I will quote Fernando for the zillionth time, who insisted on prime ideas, not maximal ideas. We will see anyway. And then if you're lucky, you develop, as you are developing, most of you, a proof theory trying to match semantic consequence with syntactic consequence arising from your proof theory. Sometimes it was the other way around. There was a proof theory, and then the algebra had to match. and we will see the big problems of matching a pre-existing calculus, modus ponens, 2,000 years old. So you cannot say, I don't like it. Well, for the next 2,500 years, they will say, I don't like you. You see, all things after 1,000 years cannot be dismissed easily. Okay, so we must be very careful about the interplay, which is extremely rich for human mind, between syntax and semantics. Syntax has the crucial property of being symbolic. You can give it to computer or to your brain for computations. Semantics is a higher level object, mathematical, algebra, order, structure, on which you can do mathematics, especially taking quotient by ideals. And then we discovered this, I would say, interesting similarity between the two oldest logics. Jump from the two-element set 0, 1, to the unity interval, which is extremely more rich and useful. Nobody knows, because there is computation theory today. So be careful about saying that the real numbers are more useful than 0, 1. We have the two oldest logics. If you look at the axioms, we were lucky to have axioms, you see that there is a minor difference which accounts for the difference between addition in the real numbers and addition in the 0, 1 set. Examples, you should have your baggage of examples. The most important are Boolean algebras. Algebras of functions with real values, which is what bookie used to make money by selling. Bookie is in fact an insurance company or a broker or somebody who sells and buys bets on continuous events. They make much more than on yes-no events. And then this characterization of Lukashevich implication. It is continuous. It respects the order. X arrow y equal 1, if and only if x smaller equal 1, and doesn't depend on the order in which your premises have been reached. Sherlock Holmes uses his premises as a set, not as a list with this is first, this is no, the set of premises. So x implies y implies z equal y implies x implies z. With this minimalist condition plus continuity, which we have seen by an objection, by a brilliant objection yesterday, seems to be necessary if you want to exchange money. When you exchange money, you never exchange an irrational number of reais. You may exchange irrationally reais, but not an irrational number of reais. So you see, rounding up is fundamental, which means you can work with continuity, just as physicists do when write down laws, instead of saying force equal mass times acceleration and with these errors. No, they don't say the error, but the errors are there. So I concluded that our honor demands that now we study this logic with passion and with our best brain, because there is so much beautiful, computational, algebraic, geometric structure that it deserves your attention, if not to say, yes, I've met Lukashevich many ways, logic, I've seen that it has many applications, I will insist on this, and I'm happy. Some of you even built the book. It's a big deal. It's a big deal because it costs almost nothing. Algebras da Lógica de Lukashevich. The people who speak Spanish. No, the people who speak Portuguese, but the people who speak Spanish, they could read it. And perhaps English people who want to learn Portuguese, hoping to be invited in Brazil. Other times, start now. I started 40 years ago, then I lost my Portuguese, unfortunately, because I have a granddaughter who speaks Spanish, you see, and then I had to speak Spanish. It's impossible for the average man to speak Italian, Spanish, and Portuguese. So I had to throw from the boat, lamentablemente, Portuguese.
Lamentavelmente.
Sì. This is the end of the summary, but I repeat, our honor demands that we start studying this beautiful part of mathematics, computer science, artificial intelligence now. Well, after the Portuguese book, with Portuguese-speaking people can read, but the others cannot, I would recommend this book on which Walter said, Groen. It's a very bad book. I remember, Walter, I will never forgive you.
So you were not sleeping by that time when I said.
I was sleepy, but I heard such a thing. I jumped. I said, how can you say that? It's written by Itala. Wait a minute. And okay, this is a wonderful book. It costs a lot of money, but
This is the last edition.
This is the last edition because it has a new edition, yes, Springer Business and so on. But this is, well.
But then really, in general, my colleagues from Latin America, they prefer to give classes using the Portuguese version.
Yes, because of you and your tremendous influence.
They think that the book is easier to
I'm
understand.
so happy. Well, as you know, I wrote my first book in Portuguese. But I knew a little bit at that time, though you did not allow me to speak Portuguese, I remember well.
Yes.
Um,
There is a story when we were finishing. We had several meetings here in Italy, in
Buenos
Argentina, and once when we were in Argentina, we tried to discuss in English, or we, in general, every day we had chosen one common language. But when Signoli's son, once when his mother arrived in the afternoon, Carmen Signoli, we heard Dario, the son, telling to the mother. They worked all during the day. But when they begin fighting, discussing, everyone speaks in his own language. And once he tried to speak Portuguese or Spanish to us, and he remembered that one of us said to him, please speak Italian, because when we speak any of our languages, it is very difficult.
Yeah.
You remember?
yes.
Speak Italian.
Only sambas and bossa novas. So, first, deep theorems, which you find in the Portuguese book and in the English book. An equation holds in all MV algebras, if and only if it holds in the standard MV algebra 0, 1. The standard MV algebra is the competitor of the two-element Boolean algebra, which is so rich in structure, order, and the operation 1 minus and addition and truncated addition and the soup. This has the same operation, maximum, minimum, but it has truncated addition and 1 minus. And it turns out that soup and inf are definable from truncated addition and subtraction and 1 minus. And then immediately, and now we are invoking mathematics of the 30s of the past century. Just after Łukasiewicz, before, in a sense, before Gödel, or contemporary to Gödel, it says then, the variety, the equational class, so the set of all algebras that obey the equations, is generated in the sense then Birkhoff proved that you can obtain any MB algebra as homomorphic image of a product of so on and so on. Never mind this. It's generated by this famous unit interval. Just as Boolean algebras, the variety is generated by the two-element set. Okay, so this is Birkhoff, but we will use it to give you a vision of formulas, equivalence classes of formulas, a concrete realization, which is very beautiful because it will allow Marcel Finger to work on his neural network. And other people to work on automated deduction. We will see all of this. My verbosity. Okay, so I promise a visualization, a concrete representation of formulas. Yesterday we saw book his truth value formulas to sell his bet. You remember, Messi will score a goal. Paris Saint-Germain will score an early goal, and so on and so on. But now we will see real Lukashevich formulas, okay? The formulas on which you can compute, on which a computer can compute. And corollary, again after Birkhoff. The free algebras were quoted ad libitum by Marcello, and so for those of you who never met free algebras, I simply let you know the algebra of all formulas is free because when you send the variables arbitrarily into the truth value, you can uniquely extend to a homomorphism. I'm repeating myself. Freeness is this. There are generators in the algebra, the variables, and however you send them to another algebra, in particular to the truth values, the extension of this arbitrary, very ugly map lift to a homomorphism. This is freeness, okay? But if you don't know the definition, free over a set of generators means there are variables, the generators, from which you can, just in the case, as in the case of formulas, lift any very bad map to a homomorphism, which is a map that respects structure to the whole algebra. And here we have, by Birkhoff, that the free MV algebra, this very beautiful object that resembles the formulas, is generated by the variables and by the operations of the standard MV algebra. Look at this picture. Oh no, it's not done. A function of a free MV algebra is just a formula up to logical equivalence. Yes, now picture. We start from the variable that Birkhoff says, let the variable be the identity or coordinate or projection function. What is the identity function? In one dimension, it is the identity function. In two dimensions, there are two identity functions. The function that sends you a point into the abscissa, and the point is sent to the ordinate. The projections, identity, coordinate function. There are three synonyms, but it is not a terrible notion. Okay, so you start from the variable. And this is Birkhoff, not yet McNaughton Marcel. Birkhoff for free, 1932 or something like that. You start from the variable, then you can turn it up by negation. Then you have not x, 1 minus x. And then you can start summing x plus not x, 1. And then you can go on with very strange functions. You get a lot, or you can take x infimum not x, and you get this hat. You go on and you get things like that. What do you get? Well, immediately you see the variable is continuous, linear, but when you take x infimum not x, it becomes piecewise linear, two pieces. And what else? The derivative, the slope, is an integer. X has slope 1. 1 minus x has slope minus 1. Look, memorize this property. Continuous, which is fundamental also for transactions, as we have seen. Piecewise linear, and each piece has integer derivatives. Minus 1 to 55, minus 55. The stuff like the third picture. The function that you get from the variables by applying the operation of the standard MV algebra is the essence of the formula. True, the computer sees the formula and starts making quadratic time, no, linear time, almost linear time computation. But the man and the woman who look at it, meditate on it geometrically and try to discover, first of all, which functions are in the free algebra. We know that they are continuous, piecewise linear, and each piece has integer coefficients. Which functions? All of them, and this is McNaughton. But first, we'll let's expel all the people who are not algebraic and who are not geometers. So please leave the academy here. Plato would say, but Plato was not such a big mathematician. What is Plato's theorem? Dieudonné would ask. Bourbaki would ask. So I write this not as an intimidation, but to alert you that now we are doing beautiful algebra and beautiful geometry, accessible to everybody, a democratic Plato academy. So we algebraize, to geometrically visualize the function and to do computation in a very sensible way, because you have full control of what formulas are, as Marcelo had yesterday. Boolean formulas, you certainly know, correspond modulo equivalence to Boolean function. Those functions on some space which only take value 1 or value 0. So the algebra, the free Boolean algebra is such an algebra. Lukashevich axiom, well, they are piecewise linear, continuous with integer code, and again, I repeat that from the identity, by manipulation, 1 minus x and infimum plus truncated sum, the operation of the standard algebra, you get very beautiful but piecewise linear continuous with integer coefficients. Continuous, finitely many pieces, integer, even in dimension 2. I will show you something. Are these conditions sufficient? So, is the free algebra made exactly of this function? Here an example in 2 variables. You do it with Mathematica, because this is already sophisticated. To do a function which has always integer slopes in the 2 dimension, and I show a density plot on the right-hand side. This is linear, piecewise linear, blah, 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 blah. I show the derivatives, okay? The direction. Well, I show the formulas from which you can see that the coefficients, we speak of coefficients, okay? The coefficients are integer, so the derivatives, the partial derivatives are integer. Does there exist a formula in Lukashevich logic for this horrible or beautiful function? Yes. The answer is this glorious theorem, 1951, Journal of Symbolic Logic, before Chang. That's life. He didn't know about MV algebra, the guy. So he couldn't say, I'm telling you what the free MV algebra is. He just said, you want to know what formulas are up to equivalence, and then he said, they are exactly the continuous function with the integer coefficient piecewise linear. And this is McNaughton theorem, and these functions are, guess which name they gave me, McNaughton functions. Okay, so much for the introduction of formulas in Lukashevich logic. Then Marcelo will do formulas with rational coefficient. Computer scientists, of course, improve the best theorems and refine them. He has a technique with 2 McNaughton functions to plug in integer coefficients. Okay, he will explain again if you ask. These are known as McNaughton functions. Here are some examples for you to fix what is the expressive power of Lukashevich logic. It may tell you not much, but we would like to stress a few functions that will be helpful to understand consequence in this logic. In any logic you do, the key notion are not formulas, are not the algebra of the formulas, but is the notion of consequence, inference. So, of course, I prepared straight lines with integer coefficients. And then I cut them at 0 and 1, and I got these functions here. Sigmoid, computer science would say, like this. They have a formula, and since they have integer coefficients, and they are continuous, and they are piecewise linear, in fact, 3 pieces, they are McNaughton functions. So there are formulas to express them, which means that you can send these formulas, if needed, to the computer to compute them. So this is the first example of a class of McNaughton function for us to study consequence in a very critical situation, as I will show you. Here is the density plot of one more McNaughton function. Here, more. This is the free algebra. It's made of such functions with their density plot, if you want to see them from above, as when you see a geographic map. Yes, as you've seen from Marcel, of course, they are a flexible tool to model neural networks. They are coded by formulas. This is the advantage. And you can give them to a computer. Computations are not more complicated than in Boolean logic, but how much more rich is the situation now? You have the real numbers, you have the rationals, you have not only 0, 1. Because of this theorem, which was hinted at by Marcello, which was proved in 87. Łukasiewicz logic, how complicated as it is, but has the same complexity as Boolean logic. This is a pleasant fact, because you have the unit interval from the viewpoint of computation doesn't add much to the complexity of the satisfaction. It's NP complete, okay? This I wanted to stress, because it's a theory. Let's recall the equation, including Kolarczyk prove that you can dispense of continuity, so that you present this extremely rich mathematical bunch with 5 easy equations. We have explained the last one is guaranteeing continuity. Now I reformulate the equations of NP algebra with implication, going back to the theorem of characterization. These are the 4 original Łukasiewicz axioms, 1920-something. Is a reformulation of NP algebras in terms of the arrow function. Nothing new, except that the arrow function is what is related to deduction for. I wrote exposition is the art of omission, because I'm sure many of you will become good teachers and good conference people. And so remember, I take it from Giancarlo Rota, exposition is the art of omission. Why did I write it here? Because Łukasiewicz wrote 5 things, but then Chang and Meredith showed that one of those 5 could be dispensed because it follows by modus ponens from the other 4. So I don't say that, oh, in fact, I said it, but I could have not have said it, and then exposition would be the art of omission for this reason of avoiding a detail. 2 fundamental notions in logic, tautologies and then consequence. Syntactic and semantic tautologies in Boolean logic. You know everything, so let me briefly, again, look at Boolean logic from the viewpoint of implication printed or sculptured on marble. It's like fundamental. Constitution of Boolean logic. A Boolean syntactic tautology follows from these 6 by replacing, by substitution and modus ponens. Nothing else follows. What you want to prove in the implication language and negation follows from this. A Boolean semantic tautology is another word. A semantic tautology is a formula of this syntactic, absolutely free algebra of formulas, which every homomorphism into the truth value evaluates to 1. It's completely different. Here we have a lifting of the jungle of the syntactic jungle of formulas into the truth values. It's everything algebraic here. A Boolean tautology is evaluated by every homomorphism to 1. How different from the mechanical definition of syntactic tautology and the algebraic, geometric, and so on in computation, and algebraic geometric definition of semantic tautology. And then a magic, probably Peirce, who knows, Post. It's the beginning of the last century. Perhaps Walter or Italy knows who showed this fundamental completeness theorem for Boolean logic. The 2 definitions gives the same set of formulas. I wouldn't be able to put a name to this fundamental theorem. Łukasiewicz logic, semantic and syntactic tautology. So we are trying to be methodical, okay? Again, on the marble, but in this case on a blue table, I list Łukasiewicz 4 axioms. And I say that a syntactic tautology, just as for Boolean algebra, is a formula that you can derive from these magic 4 formulas by substitution and modus ponens. A semantic tautology is wide different definition every homomorphism of the algebra formulas into the unit interval evaluates this formula to 1 constantly, you see? Every homomorphism, yes? Okay, and then syntactically by Rose-Rosser, algebraically by C.C. Chang, great model theorist, by the way. Rose-Rosser, strong mathematicians. 58 and 59, different proofs, syntactic tautologies equal semantic tautologies. It's a theorem where two different hemispheres are joined. The syntactic hemisphere of syntactic tautology and the semantic hemisphere of semantic tautology. However, and here we will insist, when you speak of logic, you must speak of consequence. So let's try to prove the completeness theorem for Upache's logic. Otherwise, I will not give this course. I will not dare. The classical paradigm. Note this quotation. This is Tarski, and then a German professor, I forgot first, perhaps Scholz as in Jäger, Scholz, wrote him a letter after reading probably the proofs of his book on logic, semantics, metamathematics. He read the following sentence. The sentence X follows logically. Oh, this is what everybody knows, by the way. Yeah? I'm not. The sentence X follows logically from the sentences of a class K. So K is a set of hypotheses, and you derive X logically, if and only if every model, possible world, assignment, truth valuation of the class K is also a model of the sentence X. I think you would subscribe this definition. Something is a consequence of a set of premises. If whenever you give one to all of the premises, it must give one to the consequence. Any possible world where the premises live true is a possible world where the consequence lives true. There is no possible world. The premises are true, but the pseudo-consequence is false. There are many ways to arrange it. This is so well established in logic that everybody knows this definition with model or truth valuations or possible worlds sometimes. Bolzano, another great logician and analyst, Bolzano-Weierstrass, had written a similar definition, and Tarski acknowledged the priority or the insight of Bernard Bolzano by this remark. Okay, 100 years later, earlier, 100 years later. So Bolzano and Tarski had the idea of Bolzano-Tarski consequence, the one you know. Every model of all premises must be a model of the consequence. If this is not the case, that formula is not the consequence of the set of premises. I put a De Chirico painting to show you that this definition may be obsolete for some logic. Definitions hold well for Boolean algebras and perhaps for other non-classical logic, including all logic, may fail, simply fail. The crux of the matter is the definition of model. What is a model? You evaluate all formulas, you would say, at a point, and then you look at that point if the consequence is true. But why evaluate at a point and not around yourself in an open neighborhood? Here now we have the real numbers. This is the crucial difference between, and I'll be going for half an hour on that. Yes, expect gesticulation, no, expect only theorems, but trying to make them geometric, okay? Look at De Chirico, remember, model as looking at a point. If all premises are true, I want the conclusion to be true at that point. And I ask, why not looking yourself around that point? Crucial difference. What does it mean looking around? Here we have continuity. We are in a square. We have McNaughton. I not only look if the McNaughton function is true at that point, I would like to see if it remains true, let's say, micromillimeter around it. Around it, it should be. You see, this is looking, well, we go on, of course. In propositional logic, model is truth value assignment or valuation or homomorphism by a maximal idea. A homomorphism by a maximal idea has the wonderful property that gives you a number. 1 if it is false, 0, blah, blah, blah. So a formula psi is a Bolzano-Tarski semantic consequence of a set of premises if every valuation that evaluates to 1 every premises evaluates the conclusion to 1. Evaluates means look at the Boolean function. If you think of formulas as Boolean function, the functional representation will help you a lot. We are evaluating Boolean function at point, and we hope their conclusion at that point is true, if all the premises are true. So possible word is now evaluation at a point in the domain of a Boolean function. Consequence in Boolean logic, why not? These are deep theorems. A formula, again, is a syntactic consequence of a set of formulas. Syntactic, that means computation. If it's obtainable via modus ponens, by the time-honored rules, 2,500-year-old rules. You cannot object to them. And then you have a syntactic consequence. So you want to deduce something syntactically, the computer can do it. It's co and p complete, never mind. So, small exercises, you let the computer do it, okay? A formula is Bolzano-Tarski semantic consequence if every valuation that gives 1 to each premise gives 1 to the conclusion. Observe, model is truth valuation, which is a point, a local. You don't look around yourself. Of course, Boolean algebra, what does it mean looking around in the domain of a Boolean function? The domain is totally disconnected, technically and intuitively. There are no neighbors. The only neighborhood of a point in Boolean algebra is the point itself, imagine. So you don't have to look around. Remember this. Some theorem tells that the dual space of Boolean algebra is a totally disconnected space. You don't have to look around because there is nothing around. Stone duality theorem. And the completion theorem, glory, I don't know whom, syntactic consequence equal semantic consequence in Boolean logic. So everything is good in Boolean logic, and that influenced Lukashev's logic. But, sliding floor. This theorem, which is fundamental in Boolean logic, doesn't apply, or it applies with disastrous consequences, disastrous 1 century or long consequences. It applies to Boolean logic because you are taking valuation which are quotient by maximal ideas, looking at a Boolean function at a point. And because prime ideas, the sophisticated irreducible ideas which I mentioned in defining logic, are maximal ideas. There is nothing else. Just as around a point, there is nothing in Boolean algebra. Think of the square, around this vertex, there's nothing. In 1 kilometer distance, there is another vertex. So you don't look around. In Lukashevich logic, evaluation at a point is not evaluation around that point. Prime ideas are much richer. I insist that prime ideas were mentioned repeatedly by Fernando, who is not with us. They are different from maxima. They are much more sensible. We will see what prime ideas are, okay? This is the best that Lukashevich logic gives when you study consequence. Consequence in Lukashevich logic. Psi is a syntactic consequence of a set of premises if you can derive it by modus ponens and substitution, so that 2,005 years old rules still hold for Lukashevich logic. Of course. So the computational view of syntactic consequence is the same. And then you try to say a formula is a Bolzano-Tarski consequence if every evaluation that evaluates 1, the premises evaluates 1, the conclusion. What happens? A disaster. A disaster. Syntactic consequence will not coincide with semantic consequence if we adopt this Bolzano-Tarski semantic paradigm. We will fix the problem, so I ask your patient to see, it's a beautiful geometric tour achieving completeness. So, syntactic consequence implies semantic consequence, but is not implied by semantic consequence. Methodological remark. Lukashevich logic is 100 years old. People accepted it incomplete as it is with the Bolzano-Tarski semantics without much care about why and which effect does incompleteness do to your logic. I am a Lukashevich logician, okay, it's incomplete. And then they started saying, it's strongly incomplete, but it is not complete for finite premises, and so on. But the point is that while the theory was flourishing after Chang, with a beautiful theory of primary ideals, maximal ideals, and so on, of which I will give some hints, they didn't care. They accepted a non-complete logic. Well, many logic on which we work are not complete, but this is the second oldest logic. It should be complete. It should. So there is something wrong, not in the logic, as somebody at high level said, than to retract what he had printed. But it is the fault in the semantics. The semantics for Lukashevich logic doesn't look around the point and misses the completeness theorem. If you look around, you get completeness, and you are happy. Okay, this is the methodological remark to introduce the following example from analysis 1 or from good sense will start to understanding the matter of looking around. Look at these two functions, x and x squared. Who is bigger? X. At the origin they are equal, at 1 they are equal, but otherwise x is bigger than x squared. For instance, 1/2 squared is 1/4, 1/2 is 1/2. So you see, the parabola is below. Let's try with 2x squared, with 4x squared. Oh, now the parabola is going up happily, but not near the origin. Here, look around yourself at the origin. Let's take 25x squared. Again, now the parabola jumps up, but at the origin, x dominates. It's a theorem. 1,000,000 x squared. I claim that very near the origin, if you look at it infinitesimally, or even 1 millimeter, still the parabola will be below. Are you convinced of that? Now, 1 zillion, it will be above. No, it will stay below locally. This is so because the derivative of x is 1, and the derivative of 75x squared is 2 times 75x, which at the origin is 0. So the slope is 0, whereas the other has slope 1. Slopes come in to explain why locally, may I? Yes, this function is bigger than this function. I'm sorry if you never had this, but you can compute. Okay? A variant, and now you will accept it. Look at this. Again, not x, 1 minus x, locally near the origin stays below. Always. 1,000,000, no problem. Why did I turn up? Because I want now something definable in Lukashevich logic to express the problem of failure of completeness if you only look at the point. I give you an example where now, instead of that beautiful picture, we have something definable, so you can give to the computer. And we have this green function, which is definable, and the red function, which is not x, 1 minus x. I claim that, I told you that they are definable before, so there are formulas. So you can ask the computer, give me many of these until it goes below 1 minus x. I could ask the computer, and the computer, 1 zillion, yes, It's above, it's above God. It's never below. For the same reason that these sigmoidal functions are 0 at the origin, whereas minus x is minus 1. The same phenomenon we have analytically for parabolas is now for this definable function in Lukashevich logic. And this is the crux of the problem of incompleteness. Observe. One would say that, no, don't observe. This example will help us to understand why Bolzano-Tarski semantics is different from time-honored syntactic semantics. So, a McNaughton function is a Bolzano-Tarski consequence if whenever all functions in the premises have value 1, also the function has value 1. If we go back, whenever all green functions are 1, 1 minus x is 1. You see, so technically speaking, again, let me repeat. Observe all these sigmoidal functions, trapezoidal, whatever you like. There are 3 pieces function. Go to the origin, they are all definable, there are formulas, and observe that wherever all of them are 1, and when is it that all of them are 1? At the origin. Because you could say, at point 24, all of them are 1. No, because some of them will not be 1 at point 0. You see? Only at the origin. And it is true that at the unique point where all of them are 1, not x is 1. So not x should be consequent. But what is the difference if you feel that all these green functions not only are 1 at the origin, but they are 1 also locally. All of them. And not x is not locally. This is the secret to understand why we don't have completeness and what should we do to get completeness. Let me try to go on. All McNaughton functions pi, the green function, have value 1 at 0. And so does not x. So not x is a Bolzano-Tarski consequence. But all the functions are 0 also are equal to 1 also in a neighborhood. And not x is not. So it is not a consequence in the deep natural sense we should have in Lukashevich logic. I anticipate what I syntactic consequence is binary. You obtain consequence syntactically. It would be strange if it is infinitely. The computer only accepts finite amount of information. And every syntactic consequence arises from a finite set via modus ponens. Now it comes the problem of what is the expressive power of this logic, which is able to tell you things nearby, around the point, not only at a point as Boolean logic, but around the point. This is the beauty of Lukashevich logic. What do all these functions say in Lukashevich logic? The train, look at this station train, how we relax. The train was at the station at noon, and its speed was 0, so it was standing. The train was at the station at noon, but its speed was -1. Both formulas say that the train was at the station at noon, but in the first case, the train was standing there. In the second case, the train was there, but it was moving. That's the difference, essentially. The infinite set of formulas coding the PIs says that the train was at the station at noon, and its speed was 0, because all of them keep to be true in a neighborhood of noon. Whereas not x only state that the train was at the station at noon. So the premises are not able to prove that this not x for this reason. The premises also require that the train was stably at the station for a second, for a millisecond. Whereas not x only says it could be moving. There is a speed problem here. Failure of completeness is due to the fact that the derivative of -x is -1. Well, the derivative of each premise pi is 0. Fixing the problem, yeah. Look at traffic jam. Now we are relaxing more and more. This is a picture that doesn't tell, this is Sao Paulo at noon, if you wish, or London, or Rome, Naples, ideally Naples. It doesn't tell you which cars are moving and which cars are standing. This picture, where you let the shutter to be open for a millisecond or 10 million, it tells you more. It looks around, and you see the cars that were moving and the cars that are still. Well, this is Lukashevich logic. Boolean logic shots at a point because there is nothing near. Lukashevich logic makes a more refined, well, fuzzy, if you wish, but this shot, but tells you the information about which cars are moving, which are not. In classical logic, one decides by point-wise evaluation. A shot like this is enough. In Lukashevich logic, you must look around. How much around? Infinitesimally. We have met infinitesimals already. Okay, so we can express dynamic properties of event. The train was there at noon, but it was moving. The train was there at noon, and it was still. It was there. Speed 0. Lukashevich logic has this tremendous power. The Bolzano-Tarski paradigm is punctual, too much local, cannot express this. That's the root of incompleteness. 1 century of Lukashevich logic without understanding this obvious fact. Now you understand it at the very beginning of your career. Again, in Lukashevich logic, semantic consequence differs from syntactic consequence. The latter, syntactic, well, blah, blah. Now we introduce stable consequence, which looks around. Okay? Stable means I'm not only interested in that point, if I'm true or false, I'm interested if I'm stably true. And if I'm stably true, I want the conclusion to be stably true as well. This is completeness theorem in with poles. Stable consequence. I call this stable consequence or differential consequence, but I know the differential is already intimidating, so I called it stable consequence. So I give you the definition. And compare with the Bolzano-Tarski, okay? Perhaps your logic needs stability if there is a set of truth values and a set of domains of definition which is continuous or connected. Perhaps. A formula is a stable consequence of a set of premises if every model of every premise is also a model of P, and this is Bolzano-Tarski. Plus, and whenever all formulas in P remain infinitesimally true in a direction, so does F. This is the novelty. So you don't ask, I want you conclusion to be true if all the premises are true. I ask this, but I also ask, if the premises happen to be stably true in a direction, and here, McNaughton function, you can derive them in a direction, I want you conclusion to be stably true. That's all. That's all false. In symbols, blah, blah, blah. Forget the symbols. If you understand this, you are asking not only Bolzano-Tarski, you are asking stability. Look around. If around they are stably true, I want the conclusion to be stably true. Perhaps not as much as the premises are, but locally. The derivative. I look at the derivative. Look at the derivative. Magic. Velocity. This is fundamental because now it applies to derivative. Note, these directional derivatives exist because the functions are piecewise linear. Okay?
Does this metaphor extend beyond speed? Is there any sense to talk about a second derivative? Like acceleration?
Well, you're asking too much. Yes, but in a different sense. So, private discussion between the two of us. Okay? Private discussion. I will tell you, yes, there are second order derivatives in a following sense. Not only you look at the derivative in the direction, but having ascertained that in this direction they are stably true, you must look in perpendicular direction if near the point they are still stably true. So you're looking for directional derivative and locally at directional derivative in a perpendicular, this was a classification, blah, 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 personal conversation. Okay, very good question. Second order, we are piecewise linear, don't expect much from second order derivatives, but expect much from orthogonal. Okay, personal discussion. Again, the dynamics of a material point does not depend by position only, depends on position and speed. Look at that stone, David's stone, which is to be from. It depends on position and speed, where it will go. Instantaneous speed derivatives, saying that f is a semantic consequence of a set capital F, means two conditions. Whenever all premises are true, also the conclusion is true, and this is Bolzano-Tarski, plus whenever a derivative of a premise is zero along a direction, and also around blah, 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 whatever, then so is the conclusion. Well, to make them rigorous, I will speak of, yes, really this time I'm speaking of prime ideals. They are so important, also known as irreducible, that I will tell you something. After all, Plato, who didn't know what they are, but Fernando stressed their importance, Plato will forgive me. Okay, I'm speaking about derivatives now in algebraic terms, which is better for the computer. I have a quotation that C.C. Chang, the great model theorist, when I asked him to participate in a special issue of Studia Logica on MV algebras, his creation, he wrote to me, this is Chang in Rome in 1971, by the way. The best photo you have on Chang. If you go on Google, you find ugly photo of this man. In Rome at the Encyclopedia Treccani was this man, civilized, extremely refined man. He said, he proved the completeness of Lukashev's logic of tautologies, not of consequence, but of tautologies. And he said, in the first paper in the Transactions of the American Mathematical Society in 1958, I tried. And I tried by taking maximal quotients. And I didn't get it. The papers are two. The proof of completeness in the of tautologies is in the second paper, 1959. Dana Scott, another great logician, told me, hey, CC, why don't you look at prime ideals? He didn't tell him, why don't you look at direction, because probably Chang didn't know mechanical theory. He said, why don't you look at prime ideals, which means, why don't you look at directions? And then, by a lucky break occurred when Dana Scott realized with far-reaching insight that there is a notion of a prime ideal, so you will be eager to know what it is. In MV algebra, a notion I have not considered until then, a notion that for 100 years was not considered in Lukashev's logic. And then with this notion, he proved the completeness of tautologies. A formula is a tautology if and only if semantic equals syntax, okay? But for consequence, so let me tell you a few slides on prime idea, just for those of you who want to see what made Chang able to prove his fantastic completeness theorem for Lukashev's logic. An ideal is prime if when you take a quotient, the algebra is totally ordered. This is the definition. So it resembles the unit interval, except it could have infinitesimal. Totally ordered MV algebra. All ideals containing a prime ideal are prime and occur in a chain. So above a prime ideal, you have a chain of prime ideals. Second big fact. It's the same in ring theory, in some ring. Above any prime ideal, therefore, there is just one maximal. Maximal ideal are Bolzano-Tarski semantics. So prime ideals, there is a lot below, tremendous tree of ideals, but above a prime ideal there is a chain of prime ideals culminating in a maximal. We are almost finishing. Every ideal is the intersection of the prime ideals above it. Irreducibility, crucial property, algebraic. Every maximal ideal determines exactly one point in the definition of the Macnaughton function. Just as, well, okay, this is truth valuation at a point, maximal ideal. The quotient of MV algebra by a maximal is a point in the unit interval, a real truth value. Every prime ideal immediately below a maximal ideal also determine what? A direction. This geometry comes in. Maximal ideal, evaluation at a point. Maximal ideal points, prime ideals I define, determine a direction. And now you are asking, for any prime ideal where you are evaluated to 0, the conclusion must be, whether the derivative is 0, the conclusion must be 0. This is the extra algebraic condition. I will not insist too much. If you write to me, I will send you the paper on this, okay? And the perpendicular direction for second order derivatives, which are other. The prime ideals of the free algebra are labeled by points together with orthonormal directions. F belongs to a maximal ideal if its truth value is 0 at the point. Belongs to a prime ideal if the derivative is 0. So geometry and differential geometry. So, in conclusion, a Macnaughton function follows stably from a set of premises if and only if Bolzano-Tarski, whenever all premises are true, also the conclusion is true, and whenever all functions are constantly true in some direction, then also the conclusion is constantly true in that infinitesimally. I don't say how much, how long. If they have speed 0. And then the theorem, the following conditions are equivalent. F is a stable semantic consequence of a set of premises, if and only if it is a syntactic consequence. So, completeness theorem for consequence, at last, after 100 years. But it was so natural. Look around, don't look on the corollary, stable consequence is finitary, which Bolzano-Tarski was not. Because syntactic consequence is finitary. The computer accepts only limited amount of food. Okay, what happened here? Well, I will not repeat, but if you wish, you see, not x has derivative -1. All the premises at the 0, they were stably true, so not x is not a semantic conclusion in this stable sense from the premises. Okay? We started from Boole's problem of probabilistic inference. We went to definitive probabilistic consistency. We went to the analysis of consequence in Lukashev's logic, proving completeness of consequence, stable consequence, syntactic or semantic. What now? I am concluding. Ooh.
No,
Plenty of time, but I'm concluding. This is not the last slide. I thought now it was slow. Well, I could go back.
Don't worry.
If you have questions about the stable semantics that might affect your logic and your search, you know, don't hesitate. Otherwise, when I finish, I finish. Okay?
Oh, you have time.
But do I have something to say?
It depends on you or not.
My I should go back to prime ideals. And I think it does. Let's see what happens now. Conclusion, yeah. Yeah, this guy has nothing to say. Yes, I know. 7 hours and a half. So let's go back. Chang's crisis is interesting because this guy, Chang, C.C. Chang, great model theorist, tried to prove that, no, I think it's unfair. I will finish when I finish, okay? Repeat. Prime ideas are much more refined than the maximal ideas. Maximal ideas are points. Taking quotient by maximal ideal means evaluating at a point. Bolzano-Tarski semantics. This is the same in Boolean logic and in many logics. Prime ideas are much more subtle. They are smaller, and they require not only to be true, but also to be steadily true in a direction, or answering your question in a direction, and locally also in some orthogonal direction, and perhaps in some third orthogonal direction if there are many variables, sophisticated. And these are sequences of prime ideas when you look not only at a direction, but also orthogonal direction. By looking at this stability of truth in the premises and asking that the conclusion be similarly stable, you get that syntactic consequence is semantic consequence. In particular, it is finitary. You can ask the computer about semantic consequence without asking it to compute derivatives, and you're happy because at last you have a logic that you love, which is complete. You say, that was for me, like for Chang had this problem. I want to prove completeness, and I'm sticking to Bolzano-Tarski. But for Lógica logic, I don't have to do that. I have to look. He didn't speak of derivatives because in his papers there are no differential valuation. But he spoke of prime ideals. He was the one who insisted on the role of prime ideals to prove the completeness for tautologies, but not for consequence. For consequence, it's more refined. Okay? Well, the situation of prime ideals, please remember it or read the book. Yeah, there are. And the completeness theorem, yes, which I published to honor Peter Hayek, the great logician, fuzzy logician, no, the man who did the tremendous work in arithmetic, the man who wrote Meta-Mathematics of Fuzzy Logic, a treatise of hard mathematics about fuzziness, where Pacheco's logic is fundamental, but like intuitionism and like product logic and many other logic for probability and so on. There was a book to honor this man, who is now unfortunately dead, and contributions of many people. I contributed by proving the completeness of Pacheco's logic. Conclusions. We have only touched the rudiments of M.V. and Lukashevich logic, the rudiments. Though we have proved completeness theorem for tautologies, completeness theorem for a consequence, representation of function, aspect of the functions, and equational characterization, quite a lot of stuff, but there is much more. It is a wonderful field of research. If you are interested, there are connections with quantum mechanics. This is not quantum logic. This is a logic which captures algebras of quantum mechanics 100% via categorical equivalence. So if you like C-star algebra or quantum mechanics, write to me and I will tell you how you can go from MV algebras first to ordered groups, and then using Grothendieck, again Fernando, Grothendieck K functor, you go to quantum mechanics, to the algebras of quantum mechanics. And MV algebras are a powerful tool for that. They are also in ordered algebraic structure. For those of you who do ordered groups or ordered rings, C-star algebras, and geometry, starting from the piecewise nature of every formula, of every McNaughton function. Formulas up to equivalence are polyhedra, as Marcelo will have insisted. You work on rational polyhedra. This is the book, big deal, don't say it here. This is the book that Walter didn't like.
I was trying to test you.
You should study it. And this is the book after that book. criticized because there is not even the definition of NV algebra. Itala, I wrote a book on NV algebras without giving the definition, but I said this book is a continuation of the other.
Buy the first one, please. That's three.
Moreover, Lukashevich logic and NV algebras have application in automated deduction. I will give you the books. Computer science, fault-tolerant search. Remember the satellite error correcting codes, which was helpful to us to introduce many values in nature, and then say what are the properties of many values, and we got the axioms of NV algebra. Then we started studying NV algebra independently of that, but the applications are there. This is a book by Rainer Helle, who is the teacher of one of the participants, who's not here, of course. And this is a book by a student of mine, Cicalese, computer scientist, about fault-tolerant search algorithms. And this is a book on Hayek, the great mathematician, on meta-mathematics of fuzzy logic. Again, it's not to intimidate you, but it is to show that this non-classical logic has so many ramifications that certainly will overlap with your research sooner or later. We've seen many valuedness, it's not Lukashevich, many valuedness we have seen offer course. Many valuedness is everywhere. Last but not least, today, Lukashevich logic and NV algebras have thriving applications in networks, neural networks, AI, and soft computing. There is a Salerno school cited by Marcello, Dinola, Amato, Gerla, and other people in Salerno, now younger people. And there is the great team at USB, which I've heard about these days, is collaborating. Course number 8 in this school, the last course. Do not hesitate to write to me for if you need further documentation or if you like to put questions and you want to better understand this orthogonal derivative, to understand prime ideals, and so on. So, this course, if you remember, was started with the name, well, we started with pictures. 1985, Logical Opium Campinas, probably organized by you, I imagine, at the end of a hard period for Brazil. Also now,
It was organized by Paulo.
yeah, and there were many European important logicians, and there were the creme of the creme, I would say, of South America.
Dedicated to Aida Huda. She had just passed away.
Yes. It was already starred by Newton, who was a star already in 85. And I would like to repeat this poetry by Lars Ericsson, alias, imagine who, Newton himself. The poet does not get worried. It's a bad translation because I know Portuguese so badly. I did it with Google Translate. The poet doesn't get worried with contradiction, with inconsistency. He dominates it, playing with it. In this, he resembles God. And then I said, but while a poet is resembling God, other people make money with inconsistency. Newton wrote this Sistemas Formais Inconsistentes, which was quoted repeatedly. And I would like to tell you some excerpts from some small passages from this book, because they are good to finalize my talk. There is the Portuguese in gray and the translation. It is often the case that mathematical constructions prima facie look extravagant, Lukashevich logic, and singular, widen their scope after, find applications, and eventually turn out to be commonplace. It goes on, for instance, non-Euclidean geometries. That was the beginning of model theory, by the way, the real motivation. Let's try to see what a model is, Tarski and so on, Chang Kiesler, many-valued logic, and n-dimensional geometry. These were the three paradigmatic examples given by Newton about curiosities in mathematics that then become established facts. These considerations confirm once more the insight of Cantor's genius, the essence of, and this is good for you who are younger, the essence of mathematics should motivate your research. Of course, also the need of eat or some money, of course. But if you follow this principle, that the essence of your work is rooted in its complete freedom, even if your boss is not of the idea, try hard. So, dear Newton, you have spent most of your life to apply Cantor aphorism. The essence of mathematics is rooted in its freedom. You have expanded for us the realm of logic without dismissing the classical one, the mother of all logic, by showing that its scope is quite limited and that we must be able to bring car with inconsistency, just as the poet does, just as you do. So thanks, Newton, and thank you.
May I kiss you? Let's kiss Daniele on behalf of all of them.
Question? No, no question. Question? No. Questions? Are we No, it's such a pleasant atmosphere. Don't ask questions. Private discussion. Private. Email. Yeah. Or ask questions. Yeah. Chairman.